Okay, it's good to be here and speaking at this today seems to be focused on twisted bilayers of a variety of kinds, so it should be quite focused and nice. Okay, so I'm going to tell you about a particular sort of creature in the zoo, which is twisted structures made out of bilayer graphene, and I'll tell you about some of our experiments where we can measure gaps and also bandwidths by doing transport measurements. So unusual thing is bandwidths are typically hard to access in transport experiments. I'll try to tell you a little bit about what's interesting. Our system is on the verge of being a correlated system, and I'll explain what it means as we go along. Okay, so I gratefully acknowledge the support that makes this work possible from Department of Atomic Energy and Department of Science and Technology. Okay, so I want to acknowledge my collaborators in this experimental and sort of combined collaboration with theory. So the students who have led the work, Pratap and Subhajit, are here at this meeting, and they have posters. If you have more questions, I think they'll be happy to give you all kinds of details. For theory, we collaborate for many years with Rajdeep, my colleague at TIFR, and in this particular project, we have collaborated with his student Unmesh, who's also here, and he knows a fair bit. So for some of the boron nitride, actually all of the boron nitride that we use, we collaborate with these guys, Taniguchi and Watanabe at NIMS Tsukuba. Okay, so this work is possible because of all my collaborators. This is Pratap and Subhajit right here. Okay, so this is my outline for my talk. I'm going to give you a sort of a broad introduction, why few layers of graphene are interesting. This is an area that we have been working on for the last several years. Then I'll kind of go to twisted bilayer system and briefly review. I won't really spend a lot of time. If you follow arXiv, you probably know that there is a kind of a torrent of new results coming every day. Then I'll talk about our system, what's new and different, what can we learn from it, and what are the other interesting things that one can do. And then I'll put all of this together and explain to you how we can understand this sort of metal insulator transitions in specifically in this system very comprehensively. Okay, so everybody kind of knows about graphene, which has been kind of extensively studied. But what one finds that the dispersion relation for the charge carriers actually, as you increase the number of layers, flattens out. So to see the physics of interactions in case of monolayer graphene, one had to go to really very difficult experimental situations like very large magnetic fields to see signatures of interactions for monolayer graphene. As you flatten out the dispersion of the charge carriers, which happens for, this is the number of layers, so this is bilayer, trilayer, and four layer. The dispersion becomes flatter, and in certain sectors of the Brillouin zone, if one positions the system appropriately using different experimental knobs, one can start to see interactions relatively easily. So that's one of the reasons why people have been focusing in the last, I would say, 6 years or so, a lot on systems which are a few layers. Interactions become important. The other important knob that one gets in contrast with graphene is sometimes you have knobs which can tune symmetries like electric field, which is a very powerful knob, and it'll also become clear later during this talk. There are, of course, proposals for and lots of tantalizing new results which say that you can explore physics, which has been kind of difficult to explore in other systems. But so today's focus is primarily on the moire superlattices, which are formed when you twist two layers relative to each other. This is really a kind of a new tool which isn't really available in the past experimental studies of condensed matter systems. So it's really been used extensively in the last couple of years. So these degrees of sort of knobs that experimentalists have allow new exploration, which is not really possible in monolayer graphene. So, just to give you a brief idea, it can also be used to study interesting physics. So, for example, we've spent a fair bit of time looking at different aspects of a tri-layer system, which is also an important system in this sort of family, which has a gapped Dirac band and a gapped bilayer-like band, which is coexisting. And so if one wants to study the physics of quantum oscillations and Berry's phase, this is really a kind of a nice system to look at, and we have explored this in the past. So few layers offer different sort of things for different people depending on what you're interested in. So here we explored what's happening to the Berry's phase across the Dirac band gap. And I won't really talk much about it here. But this is a really nice convenience system. The gaps are all tunable by electric field, which is perpendicular to the plane of the system. So that really makes tweaking things easier. If you think about Weil systems, you can't really, the typical Weil systems, you can't really do a whole lot. You have to kind of make new Weil system for every kind of realization that you want. So these are flexible. I want to start off by this kind of example, which will play a key role in the later part of my talk. If you look at a simple bilayer graphene, these are kind of older studies on bilayer graphene. Pristine bilayer graphene is a semi-metal with a kind of quadratic dispersion. But if you apply a perpendicular electric field using two electrostatic gates, what you can see is that you can gap out the spectrum, and the semi-metal becomes a semiconductor with a tunable band gap, and the band gap is actually a function, monotonic function of the electric field that you've applied. You'll also see something interesting here is that the bands also start to flatten out as the gap opens up. So this fact that there is a band gap can be simply understood from seeing that the electric field essentially breaks an inversion symmetry inside the unit cell of the bilayer. And once you break that symmetry by using the electric field, you have a gapped system. Okay, so this knob of electric field is a very powerful knob, and it can be used to great effect in few layer graphene systems. Of course, there have been lots of proposals and really very nice experimental results in the last, I would say, 5 to 6 months, where few layers of graphene and also twisted bilayer. I just give you one example. This was a theory proposal where you have an ABC trilayer, and you can realize some non-trivial churn bands in the system. And I think some version of this has already been experimentally observed. Of course, today, sort of my talk kind of centers around twisted structures where when you twist two layers relative to each other, even if they're made of the same system, it develops a periodicity. And that's the Moiré periodicity. And that kind of fundamentally changes the band structure. So this is really a kind of a very nice, powerful experiment done at MIT, where they observed that you have twisted graphene, monolayer graphene, twisted on top of each other by about 1.1 degree, and you get bands which are very, very flat. Okay, and the flatness of the band is in some sense a function of the relative twist angle. Once you have, what these guys' main observation was that you not just get an insulating state, but around the insulating state, you can also get a superconducting state. And that's because the bands become really, really flat and are really amenable to observation of electronic interactions. More recent results where some additional symmetries are broken, you can see many of these kind of superconducting dome-like structures at different fillings of the band. So what these systems are really showing is that you have a nice knob to control the degrees of freedom, tweak them, and look at their effects. So these both experiments that I show you are from twisted bilayer. The reason I emphasize is that the terminology can be confusing in this field. It's monolayer twisted on monolayer. And there's the thing that I'll talk more about today, which is twisted double bilayer. It's a bilayer graphene twisted on bilayer. Okay, you take a layer of bilayer graphene, you cut it, and you rotate one piece relative to the other by about 1.1, whatever your sort of heart's desire, and you kind of stack them on top of each other. And there have been some experiments earlier this year which showed some interesting aspects, and I'll talk more about it later during this talk. So what they basically see is a system with an additional tunability, because I showed you the bilayer, intrinsic bilayer system, which is sort of the building block which makes this system, is itself tunable with a perpendicular electric field, which is not the case for monolayer graphene on monolayer graphene. Okay, it's not such a powerful knob. What people, this is work from Philip Kim's, sorry, this is from Pablo's group at MIT, this is from Philip Kim's group. What they basically see is a system which has Moiré gaps. These are the Moiré gaps. I'll go to the phenomenology a little bit carefully when I explain our experiments. And beyond that, they see correlated gaps, which are this at half filling of the Moiré band. And at least the conclusion of some of the experiments is that you get a magnetic insulator, and you can also get a superconductor, which is kind of a little bit of an iffy proposal, but nevertheless, it's out there on arXiv. Okay. So these systems are more kind of convenient to play with, and I'll kind of show that. This is also our system that we have explored, kind of looked at sort of details of the band structure a little bit more carefully. So as I explained, this is twisted double bilayer. Okay, so this nomenclature in this field is a little bit important to keep track of. And you twist them with each relative to each other by an angle that you want. You get inhomogeneities in the system, so you can get an angle which varies over space as you stack it. Let's say if you have a 10 micron long device, you can have some inhomogeneities. And these are important to the physics, but using transport measurements, you can infer the extent of this inhomogeneities of angle that plays an important role in the physics. I think probably Abhay might talk about in greater detail about spatially imaging these inhomogeneities and how they play an important role later today. So this is our system. So this is what, if I measure the resistance of the system as a function of density and electric field. So in this device that I showed you, there are two gates. They allow us to apply independent control of density and perpendicular electric field. If you have a single electrostatic gate, you cannot control density and electric field independently. But once you have these, you can have a clear control. So what you see is red regions here, this is the scale bar, are kind of insulating regions, which or rather more precisely, regions of high resistance. And these are regions of low resistance. Okay, and then there are other features. So just to sort of get the phenomenology sort of clear, a cartoon band structure looks something like this at this particular point in the parameter space. As you apply an electric field perpendicular to the two layers, in this system, you will actually split this flat band into two flat bands. Okay. And these are higher dispersing bands. And then as you go up further, you will actually close this gap completely and merge these flat bands with the dispersing bands on the top. So what these are gaps, which are basically these gaps, Moiré gaps. One is on the electron side and one is on the hole side, these red regions. And what you see is that in this particular system of twisted double bilayer, these Moiré gaps are tunable, that you can actually close them. That eventually, as you apply a perpendicular electric field, you will close these. And this is again a distinguishing feature of this system relative to the twisted bilayer graphene system. Yeah, okay, so there is a critical value. You'll see more details about it. Yeah, you'll see more details of it. It happens at a finite electric field. I'll also compare it with just a simple bilayer system. Okay, so this is just a cartoon just to get the phenomenology right. So this is a metal, blue is kind of metal-like, these red regions are insulating, and this is sort of what you should kind of think. And the important thing is it's very different from twisted bilayer. So I showed you these cartoons which are sort of simple and easy to understand the underlying physics. But Rajdeep and Unmesh and Rajdeep have kind of done detailed calculations which allowed us to actually infer this cartoon picture for the sake of simplicity. Yeah. So these are at 1.5 Kelvin, but 300 millikelvin also doesn't change much things. Temperature is a very important knob. You'll see in the next few slides. Okay, so this cartoonish picture is good enough for understanding the essence of what I'll talk about, but it's kind of borne out by calculations as well. So I use the phrase that is in the word, this particular system is on the verge of correlation. So again, this particular choice of the angle that we used in our experimental system is on the verge of correlation. Why do I say that, or why do I use this? So if I apply so there are no, let me just say, I should explain. So this band here, if I saw an insulating state here, I would say that when it's exactly half filled, I have correlated states formed. But in this system, at zero magnetic field, I don't see any gaps within the band. Okay, so that's why I say that no correlations are, strong correlations are not present. No, there is nothing. So these features are kind of consistent. These are not gaps. These are throughout all twisted bilayer. It doesn't have anything to do with the physics of interactions. We've kind of looked at it. I can explain more during tea time. Okay, so what we do is we apply an in-plane magnetic field, and the same picture changes quite a bit, and you'll see that this is the full band. This is now, you apply an in-plane magnetic field, you'll see gaps open up, feeble gaps at ns by 2, ns by 4, and ns by 3 by 4. These are small. If you want to see sort of the evolution of the gap, you can look at the slice as a function of parallel magnetic field. And you can see that you need some finite magnetic field to coax the system to develop gaps in its electronic spectrum, and these gaps are correlated gaps. So this is sort of the cartoon. What happens if I have a flat band and I apply a parallel magnetic field, I can also open up gaps. So this, in its native state, doesn't have gaps. You have to apply some tweaks to get it to form gaps, and that's really why we choose this particular realization of the angle, because we don't want any of the next set of measurements that I'll show you, bandwidth and band gaps, to be affected by any enhancement of the gaps due to correlated states. Okay, so that's our system of choice. So when we do experiments as a function of temperature, density, electric field, and these are just the response resistance measured as a function of temperature at different points in the of electric field, and as you go along the x-axis, your different doping level of this system. This is the charge neutrality point, the vertical line. Y-axis is electric field, x-axis is density. So you can position it very nicely at different points, and you can see different kinds of metal insulator transitions in the system. And these metal insulator transitions can be used to extract out important energy scales of the system. This is at one of the Moire gaps. You can actually do kind of detailed measurements, which is what Pratap and Subhajit have been doing. Yeah. We do see Landau levels. Yeah, we do. We can. This is in plane magnetic field. This won't show the Landau levels. We intentionally don't want any of the physics due to the Landau levels coming to the picture. Thanks for asking that question. So one can actually use this kind of a activated measurement to extract out various energy scales which are relevant in the system. And so this is sort of the characteristic response of the system, and you can extract out the band gaps. Now, this is the, just to get to your question, as you increase the electric field, this is the gap. The orange color one is the gap at the charge neutrality point. It, from our measurements, it doesn't sort of increase steadily from zero onwards. You have to go to some finite electric field to get it to open up. Okay. And you'll see these Moire gaps, which is blue and green for electron side Moire gap and the hole side Moire gap, and they are not exactly, they have similar behavior, but they're not the same. The Moire gaps are different in magnitude as well. So if one uses a minimal model, sort of like the model of Alan McDonald, and you'll see kind of symmetry in the system for the two Moire gaps. So it's a sort of, among many evidences that are out there, electron hole symmetry in these systems is no longer a sort of a good way to describe. So if you take kind of a detailed electron hole asymmetric model, you kind of capture sort of the asymmetry in the Moire gaps that are there. Now, just to give you a comparison, these are the gaps that are measured at the charge neutrality point of this twisted bilayer system, twisted double bilayer system that I just described to you. And this is the band gap evolution of the simple bilayer graphene as a function of electric field. So it's naturally, as one might expect, as you twist the two layers relative to each other, it doesn't really, it changes the band gaps kind of in a fundamental way. Now, one additional thing that we have been working and something that's key to understanding interactions in these systems is what happens to the bandwidths as a function of different knobs. In our case, the most powerful knob is perpendicular electric field. So in a particular part of the parameter space, so as we apply an electric field, as we open up a band gap due to the electric field, and we realize two flat bands, in this sort of regime, when you have two flat bands, you can actually write up a simple model to understand the metal insulator transition and extract out the bandwidth. So to get to the essence of the experimental system, we tune the system to this point so that it has two flat bands and sat ourselves nicely at the charge neutrality point and measured the metal insulator transition, okay, as a function of electric field. As long as we have two flat bands, we can model the system in a simplistic but I think a powerful way. Two flat bands which have kind of a simple parameter to describe their existence. Now, using this, we can kind of fit and extract out the bandwidths and say something more meaningful. So and these are all measurements done as a function of electric field, temperature, and density. And so what you see is that as you increase the magnitude of the electric field, the bandwidth increases, the band gap also increases. You can measure it. And the fact that you can measure these bandwidths using kind of transport is kind of convenient. Of course, it relies on a particular positioning ourselves in a particular part of parameter space, but it is kind of important. So over a small range of electric fields, we can go much larger. We can see that the bandwidth increases quite a bit. So typically, bandwidth measurements are done using spectroscopy, STM, and STM experiments are a little bit tricky. I think Abhay possibly will talk a lot more about it, are a little more tricky to apply electric fields and to do spectroscopy. But so this is a nice way to look at the system and track its evolution of its bandwidths in the system. So one of the things that we have been kind of looking at is when the interactions develop as we apply an in-plane magnetic field, what happens, does anything happen to the bandwidth or the band gaps? So we can kind of do similar analysis. And what we see is that as we apply, so we can, not really a whole lot happens to the bandwidth as one might expect, except that sort of G star mu B kind of gaps, which are there in a kind of due to a sort of a magnetic insulator, they broaden out the bandwidth, but in terms of the gap, we consistently see that the gaps reduce, because if you have two lobes of the flat band and you apply a magnetic field, that the lower part will move closer as you apply a magnetic field, and the upper half of the lower band will move closer, so the effective band gap will actually end up reducing, which is sort of consistent with our measurements as well. So this gives us kind of greater confidence, and the amount of splitting is kind of consistent with what theorists have predicted. So using all this information that we have experimentally extracted from our experiment analysis, this is sort of the measured sort of at charge neutrality point, at zero electric field at a varying value of density. We see a whole different sort of transitions from a metallic-like response to a more insulating-like response. We can kind of put the extracted information together and see whether it makes sense in terms of the bandwidth and the gaps. And we see that it's reasonable agreement. And the simple essence of this kind of a drop is the fact that above these flat bands, there are these dispersing bands, and they end up giving rise to this drop in resistance, because as you go to higher and higher temperatures, electrons can be activated across the gap, the Moiré gap, and you see an increase in the conductivity of the system. These are sort of contours of, I think, the peak in resistance. They're not super critical right now, but I think maybe Pratap can help me out. I can't remember now. Pratap, right? Peak. It's sort of the peak of this resistance feature tracked all the way out. So this is to delineate some trends. Okay, so that's sort of the story that I've been kind of mostly wanted to tell you. I wanted to kind of briefly advertise a poster. This is kind of a story which is being finished up now. We're also trying to explore Valley transport in this system because it has these gaps, gaps due to Moiré physics and gaps which are intrinsic to the bilayer system. And we have been using the Valley transport, which is using sort of some sort of a non-local device geometry to measure the diffusion of the Valley current over as a function of space. I don't really have a whole lot of time to discuss this, but this is kind of primarily an advertisement for a poster out there. So if you're curious, you can come and talk to me or talk to Subhajit and Pratap. You'll learn more by talking to them. So let me just quickly summarize what I promised. We've been kind of looking at this twisted double bilayer system, which I think is a little bit more powerful system because of electric field being an important knob. And we kind of understand the essence of the phenomenology that we experimentally observe. And I think the take-home message is that in certain regime of the transport measurements, we can actually extract out bandwidths by doing transport measurements. And the bandwidths are actually tunable with electric field, which is kind of indicative that electric field itself is a very powerful knob to tune the correlations in the system. So I think I'll stop here and take on any questions that you might have. Thank you.
Very nice talk. Why do I expect the bandwidth to increase with the electric field? Although individual layer, you said band became more flat. Individual band gap, when you open an individual layer, it became more flatter. But why do you expect the bandwidth increase with the electric field?
The honest answer is I don't have a simple intuitive picture for it. But people who have done ab initio calculations on these systems, they are trends measured evolution of the bandwidth is actually in very good agreement with sort of measurements done by people actually elsewhere. So I don't have a very simple picture. Maybe somebody else has. I don't have a way, but this is now kind of fairly reasonably well established.
So a second question regarding which you didn't talk about, this parallel field, you are able to see the gap opening at all integers, right? Like one.
So okay, depending on how you define it, ns by 2 is the strongest gap.
Right.
This data, yeah. ns by 2, you see the strongest gap, and ns by 4 and 3 ns by 4 also there are gaps. But they are smaller.
So what's the origin here?
These are, I think Ashwin has a theory paper out on it, but these are magnetic insulating states that are formed in the system. So as you apply in plane magnetic field, you basically polarize the system. And the gaps that are kind of incompletely formed, fully form in your system.
All the zero field, you don't see any signature.
That's right. That's exactly, that's sort of what is different. I think this somewhat related measurement has been also seen, I think, I forget, maybe Philip Kim. So the twist angle is the key thing. So depending on the twist angle, you can not have the gaps formed at zero magnetic field, but you can coax the correlations to develop by in-plane magnetic field. Yeah. Okay, good. Yeah, good question. So the only assumption is the only assumption is we assume a very peculiar, I mean, as an experimentalist, I can tell you outright that this choice of the form of the density of states of the flat band is just kind of the most simple version that we can choose. But because we didn't want to introduce 5 other parameters, because then we can fit much better, but that's really not much fun. So that's the only thing is the shape of the flat bands. Density.
All the resistances comes from activation. So the resistance is telling you the carrier density, or the you have to assume different mobilities for the flat band and the.
Yes, so we position ourselves for these extractions. We sit in the middle of the gap. So we are further. There is a Moire gap on top of it. This metal insulator transition is because of by sitting at the charge neutrality point at precisely in the middle of the 2 flat bands. So I mean, I can give you further details, or I can send you a preprint, but I think at finite densities, to understand everything, it's a little bit more complicated, and you need to take in mobilities and things like that. But at this point, at charge neutrality, you can do a reasonable extraction. You can see the error bars, but the trends that we see are much beyond what the trends are.
All right, thanks.
You can talk more.
Mandar.
Yeah. Wait, sorry. Okay.
Sorry. So you'll have still a quadratic band touching of this narrow band, right? I mean, in this case, no. So my question is that why do you get this threshold electric field? I mean, like.
Good question. I don't know the answer to. I don't know the physics answer to it. That's sort of what we experimentally observe. There are a lot of details of sort of why it's happening microscopically is unclear to us and unclear to many people who are working in the field. So I'm sure you'll be disappointed with the answer, but that's sort of the reality.
You mentioned about measuring the inhomogeneities through transport measurements, that is change in the angle over a micron order length or whatever. Is it possible to elaborate a bit more on that? And B, the R versus T at NS seems to show condo-like behavior, which seems to be tunable with the electric field, I think. So,
I mean, we don't like to use word like condo-like behavior. We just like to see metal insulator transitions. There is no reason for us to invoke any complicated physics than is needed. Now, this position of the Moire gap, I'm sure you know this, but let me, I'm just answering your first question. The position of this Moire gap, at what density it occurs when you, tells you what that twist angle is. And that's really, if you have many, many pairs of electrodes, we do see variation in that angle in the same device. This is well established. It's not really news. We're just confirming what people in the community see all the time. In these systems, no. The short answer is no.
Mandar, I have.
Yeah,
sorry, there was a lot of stuff there. It went by fast. Let me summarize what you're saying, and you correct me if I'm wrong.
Okay.
What you measured
Thanks
are
for doing that.
the single particle gaps at charge neutrality and full Moire filling, and you find that essentially, without having to deal with correlations, sort of DFT theory level, for example, agrees well with the experiments. Is that?
Ours is not even DFT. I think Rajdeep is the expert, so I deferred to him. So it's very comprehensive calculation. Maybe Unmesh can answer, but it's not DFT.
Sorry, but okay, some single particle calculation, whatever gaps they predict, matches reasonably well with the experiment.
Yeah.
Is that fair? Okay.
So I have one simple question, is that in the bilayer systems, there is a trigonal warping, which actually breaks the quadratic band into...
Yep.
Is that a tunable parameter in your system?
In a weird way, it's not a most direct way. Actually, as you tune the Fermi energy in the system, the extent of the trigonal warping becomes more and more dramatic. And I would say it's tunable in that sense. So because we can completely tune electric field and density, we can tune the Fermi energy and sample more of the trigonal warping.
I have another small question, is that what is actually the small angle that you see the flat band before tuning the fields? And
so, we make devices of several angles, but the system that for which I showed you most data today in the talk is around 1.18.
Thank you.
I think Mandar can take more questions during the break. So let us thank Mandar once again.